So we need to finish up, gosh, chapter 1. Are you serious? Yes. So, but we don't have very many to go. And so I'm going to start, take a running start at it. And is this where I wanted it? Yeah. This is the figure I wanted to pull up. Remember, we talked about this the other day, Monday. And I'm going to go ahead, and this is going to be my sun, and I am the earth, and what I hold out is the moon. So that's the sun. And so we kind of have this sort of deal where if that's the sun, I am the earth, this is the moon. What phase is the moon in here? New. Very good. You got it. How long does it take to go 1/4 for the moon to orbit the earth? About 1/4. About a week. Perfect. Speaking of quarters, what phase is the moon in here? First quarter. I'm liking it. What phase is the moon in here? Full. Perfect. Okay. And so we talked about eclipses, and we said that this actually could be an eclipse of the sun. This actually could be an eclipse of the moon. I want to talk a little more about that. But the reason it doesn't happen like that exactly is because we talked about the plane of the ecliptic. That's where the Earth is orbiting the sun. Okay. The orbit of the moon is tilted outside of the plane of the ecliptic. If it was right inside the plane, if they like coincided, the plane of the moon's orbit about the Earth with the plane of the ecliptic, we'd have eclipses all the time. Okay? So, we actually did this slide, okay, and we talked about the things cast shadows. Actually, the moon casts a shadow when we have a solar eclipse, and the Earth casts a shadow when we have a lunar eclipse, eclipse of the moon. But we have this dark part, this umbral part, and the penumbral part, kind of the lighter part. Okay. So we didn't do this slide, but actually I've got 3 types of eclipses, and I did mention on Monday, okay, that if the moon, and we have one of these coming up, somebody told me it was February, what day is it? Okay, thank you, February 10th and 11th. So we have a little bit of time. Now, if you're trying to catch an eclipse, if you're like me, you have to look at the internet and see when, okay, and then you have to look again to see when, and then you have to look again to see when, okay, because if you get the time wrong, you're screwed, okay? So we'll kind of be looking at that. But what's going to happen with that penumbral lunar eclipse is the moon is orbiting the Earth, and the moon is going to actually go into the part of the shadow that the Earth is casting called the penumbral part. Okay, umbral is dark, penumbral is light. So I think in my instructions I said you can go out there and you can get lab credit, and hopefully it'll be clear, okay? But it'll be a real subtle thing. So again, we're going to go for timing, okay? And this actually, I have some pictures here to kind of show you the 3 different types of lunar eclipses. This is trying to kind of show you the subtle, I don't know. And then we have where a bite is taken out of the moon. Now, can you see the difference between the moon here and the moon here? Okay, here the moon is actually in a lot of it is in the penumbral part, but a bite of it is in the umbral part. And this is actually where you would see a bite taken out of the moon as the moon passes into the umbral part of the Earth's shadow. Okay, but now this is the granddaddy of them all. This is a total lunar eclipse. Sometimes they call it a blood red moon, okay? Because for whatever reason, and I've kind of looked it up a little bit, but when that moon, basically when all of the moon, which used to be kind of lit by the sun, right? When all of the moon goes into the Earth's umbral part of its shadow, the moon kind of turns this kind of reddish color. Okay, and it has to do, I think, with the Earth's atmosphere kind of bending some light from the sun to get to it and all that. Okay, so.
Just
yes.
How terrifying that would be.
Yes. If you were in ancient civilization, that would be very scary, you know. So I think it's interesting. So these are some of my photos again. These, I think, I must have been taken through the telescope. But you might look at them and you're like, hey, Mrs. Snipes, those look like gibbous moons. Okay? What looks a little bit different about them? The lighting looks different. It does. The lighting looks different. Sometimes I look at this, I'm like, that looks totally flat. Yeah. And starts with the letter T, what do we call this part right here? Terminator, yes. You know, that would be the terminator if it was a gibbous, okay? But doesn't that look different than my other terminators? It looks all fuzzy, okay? But that is actually the Earth's umbral part of the Earth's shadow, okay? And the moon here is in the penumbral part, okay? This is the umbral part, okay? So I just think that is so cool.
Are those waxy?
Actually, these would all be over here. So what phase is this? They're all full. This is I didn't mean to throw you off by saying this looks like a gibbous. This is not a gibbous. This is the moon in its full phase. This is the moon in its full phase over here. This is an eclipse. Yep, this is an eclipse. And I went ahead and I think I posted the video.
The shadows would curve.
Yeah, the shadows are curvy, exactly. And that kind of makes sense because the Earth's intense shadow, the umbral part of the Earth's shadow is kind of curvy. Yep, it looks different, doesn't it? This is a full moon that has a bite out of it. I just think it is so cool. So this is leading up to what we call totality, the blood red. So, okay, so solar eclipses. So a solar eclipse happens during new moon phase if the moon is just kind of lined up just right. So this is a good one. I want to start here. So do you see the moon is going to cast a shadow onto the Earth. The moon is going to cast a shadow onto the Earth. What's the Earth doing?
Rotating.
It is rotating, exactly. So basically, as that shadow is cast on the Earth, right at the new phase, and it's just happened to be in the plane of the ecliptic, okay, the Earth is spinning, so you get this kind of region on kind of a path as the Earth rotates where it's going to see this solar eclipse. Okay, I'm going to show you that path here in a minute that's coming up in August. So there are a couple types of solar eclipses too. Okay, so if it totally blocks out, and in August 21st of this year, 2017, we actually, if you have to go a little bit south of here, you can be in the path of totality. So the path of totality is, here's the sun's disk, okay, here's the moon orbiting the Earth, okay, it basically, this disk goes in front of the sun, okay, totality. There are some really cool science things that people can do at totality because you figure it's blocking a lot of intense rays that we're used to just, the sun is, never look at the sun, okay? So at totality, a lot of that direct radiation, it's safe now to do some experiments that, you know, not very, it doesn't take very, you don't have very long. Was it Newton or Einstein? Must have been Einstein, sorry. Albert Einstein actually traveled to someplace in South America, I want to say, to catch a total solar eclipse so that he could actually look at a star beyond the sun. As the sun's in the sky, we can't see stars. Okay, you block it out and you have a fighting chance to see that star. I think I got that right. And then he actually could prove one of his ideas about how objects warp the fabric of space and time. That is so cool. I know. Okay, so that's a total eclipse. This is a partial solar eclipse, and I have a picture of this coming up. The difference here is kind of like a partial lunar eclipse, where basically, if this disk is the sun, the moon is kind of not entirely blocking out the entire disk. Okay, this one actually, you, at totality, or you don't get any totality. You don't get a whole thing like this. It's kind of like this. We have one more type of eclipse, and it has to do with the fact that, well, I'll put it this way. If I'm the Earth and this is the moon, is this distance always the same? No. Okay, so, and I kind of have to think about this. If the moon's a little bit farther away, basically it won't entirely cover the disk of the sun because it's a little farther away. It's a little closer, then it actually would cover more than the sun. Okay, as it gets farther away, relatively speaking, its angular size is less as it gets farther away. So this is actually, that totality, you won't really have totality. You'll basically see a little rim of the sun because the distance is a little bit greater. Because we talked about perigee and apogee.
So if you're not in the path, so I'm like, I stay right here when
Right.
it's supposed to happen, will it be a partial solar eclipse?
Yes, I'm pretty sure, I'll double check that. But she asked if you're not in the path, you're a little outside of the path of totality, are you going to be able to see one of these? And I'm pretty sure yes. Yep, I need to double check that. I know. And in case I forget to say anything, I think this is right. You might look it up on the internet because I never want you guys to hurt your eyes or anything. But I think If you end up being here, August 21st, I think it's August 21st, use welder glasses, like welder stuff you hold up to the sun, and then you can safely watch it. Okay? You can also buy these, they're like $1.50 or something like that, eclipse glasses. So this is actually, this was a partial eclipse, and what was the weather like? Cloudy. And I'm thinking, is this right? I think these were taken through my telescope too. You kind of see, if I look at the sun through my telescope, this is kind of what I see. Now, obviously, if this is the optical tube of my telescope, we're going to put our eye down here. To look at the sun, what I have, and I'm going to drag it out here for one of our labs, is I've got this filter that looks like I have a glass one now, that looks like a welder glass, okay? It goes over here. So that when we look at it, the sun, and when I take those pictures, it's safe for the camera and safe for our eyes. But you can clearly see the moon going towards its new phase, taking a bite out of the solar disk. Okay, so this one wasn't a total solar eclipse. I did fight the clouds. So this is showing you a famous place, and you see the sun actually at totality in the center, and you can see the bites being taken out of the sun by the moon, and then it kind of recovers. This goes through the year 2038, and you can kind of see the paths. So those, by the way, that's not very many for that many years, is it? Let me pull up my marker here. Let's find us, because it's all about us, right? Okay, yep. So we're there, kind of there, about there-ish. Here's my August 21st eclipse, and I'm going to kind of show you what that looks like here in a minute. But you have to be there, or if you're not there, you're going to see a partial solar eclipse, which is pretty cool too. Okay. So I think, if I haven't yet, I'll double check that this is out there on Twitter. But there's so many websites. I think I chose one that's a NASA website. There are so many websites that are gearing up for this total solar eclipse. There's even Facebook sites, right? And I think I might have told you that my husband and I have a room in, where is it? It's not far from St. Joe. But when I called St. Joe, like this fall, to get a room for next fall, they were all sold out. You're like, really? So anyway, yeah, it's a big, hairy deal. It's the first day back for teachers, not students. I think you guys are still. Okay, so there it is. I'm going to go ahead and zoom in.
Oh, that's the August one?
This is the August one, yep. So where are we?
A little bit north.
A little bit north still.
Very little. St. Louis isn't too far.
Yeah, St. Louis isn't too far. I'm kind of disoriented. St. Louis.
A little bit north.
I need to go farther north for us.
Right about there.
Oh, I see. There's Quincy and Hannibal. I'm going to zoom in a little more. So you don't have to go too far south. There's Bowling Green. Where are we? Come on, are you serious? You keep saying go north. Oh, there we are. There's Fort Madison and Keokuk. Thank you. Whew. Okay. So yeah.
So the red line is where you're gonna see it like the north of Paris?
Right. I need to double check how that works, and I could be wrong. I don't know. I don't know.
Yeah, I wonder if it matters the time also, like since it's in different
Yes,
spots.
yes.
So
And
like, when we get to that point, like view at that point.
right. And that's where you check the time, you check it quick, you check it, and you recheck it. So yeah, if you're catching it over there, it's going to be different than if you're catching it over here, because the Earth is spinning and the whole time thing hurts my brain. But you want to be careful. You are where you need to be. Yeah, and I'll double check that. I'm pretty sure that this whole area sees a total eclipse. I think the farther you are from the midpoint, the shorter the total eclipse. But it does go through totality. And then anything kind of, we should find another map that kind of goes like this and says how far out you'll at least get a partial eclipse. So we'll have to work that. That is so fun. But this class will be over. Sigh. When that happens. Let's see. I got too many things open. Maybe it was here. So my next slide says, oh, yeah. All my next slide says is this. Maybe? Okay. So you're going to save the last 3 slides, okay, of this chapter, and we're going to insert them in chapter 3. So go ahead and turn the page to chapter 3. And we'll see what we got. What was that? What was that movie that came out? And I can't remember what actress was in it. She's famous. Yes, thank you. This reminds me of that movie Gravity. Stranded. You're like, are you serious? Yeah. This is amazing. So this is like a photo of an astronaut. Okay. Now, the skies are blue. The Earth, not all planets have blue skies during the daytime. Okay, our sky at night's not blue. Okay, but during the daytime, what happens is the Earth's atmosphere scatters light from the sun and makes it blue. So if a planet doesn't have an atmosphere, no blue skies. Okay. So anyway, so this is the little bit, you can kind of see the Earth's surface, and our atmosphere is so thin, it's just amazing. Okay. Oops, I guess I need to do this. All right. So this one goes a little bit historic, and the older I get, the more I'm interested in history. I like to hear that there are young people that sometimes already have that passion for history. One of the things in science, we're going to talk about the scientific method, I love in science is that we don't reinvent the wheel, so to speak. I mean, we build on what others know. And one of the things we're going to talk about here is the history of astronomy, and it's definitely kind of passed the baton from here to here to here. I think I am going to go ahead and play this little video for you. For this, down here is the the Library of Alexandria was crushed. I can't remember who did it. You probably know.
Quite a few people actually.
Okay, but it's like, and I almost feel like we're in a climate that way again sometimes, where science and knowledge, it's like, who needs that, you know? Let's go destroy it. You're like, really? I think we should look at it. So anyway, so this is, it was a great library where folks were trying to have a central repository for knowledge. And so I'm going to let one of my favorite astrophysicists hopefully tell you about it. And when you hear his voice, cry out, what is his name? And you probably already know I said my favorite astrophysicist. At University of Iowa as a guest speaker, and I went. So our daughter was there, and I was like, okay. So, yeah. These next slides kind of talk you through specifically what were people interested in. Now, I already told you that, you know, before there were smartphones, before there were computers, before there were televisions, before there were radios, okay, people probably did different things for fun than we do now, okay? But now this isn't necessarily for fun. This is a practical thing. And I actually pushed a link out to this website. What sort of moon is this, by the way? Is it a crescent or is it a gibbous? The moon up here. Like those circles are the moon. What do you think? It's a crescent. Yeah, it is a crescent. Looks like a little crescent roll. And depending upon what latitude you're at relative to the equator, and also depending upon the time of year, actually kind of the tilt of the moon's orbit about outside the plane of the ecliptic, you'll actually kind of see the crescent in its different sort of forms. So you can do that. Actually, folks here in Nigeria did that to understand when their rainy season would be. All right. Important. Stonehenge. Okay. Ooh, right? So I actually, yesterday, I did some Googling of Stonehenge, and I put out a few articles I thought was interesting. Stonehenge is very, very, very old. And there's a map that I posted on the Twitter feed that basically has Stonehenge, and it shows you some of the important points in Stonehenge. But it it's amazing that that long ago, they could take those massive stones and position them, for instance, such that during a solar, not eclipse, during the
Solstice.
thank you, during the solstices, the sun would actually come through the center and go over here to a certain point. It's like, yes, through the gap in the rocks. And it points over here, so I have a map to kind of show you that. And then during the other solstice, it would come through another direction. Just this sweet, important points of the seasons as the Earth orbits the sun. Okay, I know, I just think that's amazing. We've got a few kind of like that. This, and I had to research what an obelisk is, but an obelisk is basically a solid piece of stone that goes vertical. And if I read this right, the biggest obelisk, the tallest obelisk, actually is the National Monument. So they don't, I'm like, that's interesting. I know. Have you guys seen sundials before? Okay, basically what it does is it says where the sun is and then where it's casting the shadow. That's the time of day. So this is actually an obelisk outside the Vatican that actually also serves as a sundial. So I think that's kind of fun. And by the way, that obelisk, actually it was relocated, and it's just amazing to think that people so long ago could relocate an object like that. It just totally freaks me out. This is an old-timey thing, and I wonder, I might go ahead, no, I'll just kind of leave you to go to the Twitter feed if you want to. But this is very old, and you're like, what's the big deal about this? It's very simple, too. In a cave, it has this is kind of like you kind of see the little circle thing going out. That was etched in the stone. And then outside of this are 3 kind of slabs that are placed strategically so that, again, during the solstices, that sun dagger goes through a particular place on that picture of a sun. I know. I'm like, that's just, how did they do that? It's amazing. It's so very old. And then there's this one. And this one I read yesterday that if you want to get here, good luck. No. If you want to get here, you have to, take the plane or whatever, get this one location. Then you have to take a bus to get to this other location. And then you take, I don't know, was it like donkey or something to take a 3-day hike here. This is very remote. Yeah. So I thought that was kind of cool. And again, it's got some very important, how it was built was to honor or to recognize these important times of the year. This last one's kind of neat. This is actually what travelers in Polynesian travelers would use to get themselves between the islands. And I was reading yesterday that they actually, you guys are familiar with the constellation Leo, maybe? Yeah. They would actually use, you could use the North Star to kind of navigate, but say things are kind of such that that's not practical. You can hold this up to where Leo is and kind of know which direction you're going. So you match those beads up to the stars. So I thought that's kind of cool. It's all cool. We're going to talk ultimately about the scientific method, and I kind of say the scientific method is, that's where you have observations, you develop a hypothesis, you do experimentations and all that, and maybe you can elevate your hypothesis to a theory. Now, when did that start? Well, it started after kind of what this slide is talking about. It wasn't 500 BC, but clear back then we had philosophers and kind of budding scientists, okay? So one such budding scientist did this sort of thing. I was trying to think how to do this. So Syene, the city of Syene, the city of Alexandria, okay, notice they're at similar lines of longitude, but they're different latitudes. So at a particular day, and I didn't double check that Syene maybe is at that Tropic of Cancer, because at 23.5 degrees north latitude, you get the direct angle of the light on the summer solstice. But anyway, So what they did, I just think that's amazing. They had the sun here, okay, and it was directly overhead here, okay, but over here, as you go up in latitude, it cast a shadow, okay? Now, the angle of the shadow it cast is an indication of kind of how far away it is. Not only that, but it's on a curvature. That's kind of why they don't have the same shadow. It's because it's curved here, up here in Alexandria. Okay, it's not like this, it's like this. Okay, so it casts a shadow. And they could use that angle and mathematics and this distance here to get to what is it to the center of the earth. Is that not cool or what? Okay? I just think that is amazing. Does this make sense? This is the point, they knew that the earth was round at that point, right? Okay, there were other things to suggest that, but earth's not flat or the shadows would have been the same. Okay. Now, so here's the deal. Now, you came to this class having a sense for the planets, the order of the planets, okay? The order of the planets, and that all the planets orbit the sun, right? This is the sun, the planets orbit the sun, okay? Now we're gonna actually, if I go right here, I think I'm gonna put this on the board. You came to this class thinking that, is this the sun? It is the sun. Let's see, it's Polaris, so this is winter, so we're gonna kind of make our, kind of go like that. Okay, and that's the path of the planets that orbit the sun. That could be the Earth, it could be one of the other planets. We actually call this the geocentric model of the solar system. Darn it, are you serious? I can't believe I did that. Oh, we call this the helio. Okay, final answer. Sometimes called the sun-centered. Okay, now, switching gears, this one right here, I'll put the rest of this. And I was thinking about this little bit ago. What's this called, this rubber thing, which I did look, I priced it, I'm getting closer to ordering one. Okay, what is the plastic part? There's letter C.
Oh, the celestial sphere.
Yeah, it's the celestial sphere, yeah. So for the longest time, I'm gonna draw another one over there, I'm gonna call that the geocentric. For the longest time, I'll scare you. Okay. Okay. For the longest time, people thought that the earth was here and the sun orbited the earth, and this will be the sun, and actually all the stars orbited the earth, okay, and they thought that the other planets orbited the earth. I'm kind of drawing it going clockwise, but that's okay. And this was the geocentric model, final answer. Sometimes called the earth-centered. And it kind of makes sense. Oh, we could throw the moon in there, okay? Moon. Okay. Yeah. Notice though that back as far as 260 BC, in fact, I think I'll go ahead under heliocentric. I'm going to go ahead and give him credit. I'm going to put Aristarchus. And I'll go ahead and put about 260 BC. That's a long time ago. Okay, he was with this sun-centered model. Also under the, or I didn't also, but over here under the geocentric model, I'm going to go ahead and put Ptolemy. Claudius C. Ptolemy. The P is silent. Okay, and he was 100 to 700 AD. I kind of think of Ptolemy as a kind of the last person to kind of really talk about this kind of Earth-centered or geocentric model. And the way he did it was, and I'm going to have to talk about what retrograde motion of the planets are. If you're like an astrologer person, like you might already kind of hear this idea of retrograde motion of the planets. You guys remember we can see Venus right now in the nighttime sky. In the nighttime sky we can also see Mars. And they usually go, what we say direct motion, but sometimes they go backwards, and that's what we call retrograde motion. So the retrograde motion I'm going to talk you through here in a minute. Actually, this has got to be Earth-centered, okay? And this orange thing is the planet that's orbiting the Earth. Really? Okay. Now, this direction, this motion, kind of from, I guess it kind of looks to me from right to left. This motion from right to left is what we call direct motion. That's direct. Okay, that's direct. This would be more direct down here. What is indirect or retrograde is this right here. Planet goes like that. Planet goes like that. Planet goes like that. My point here is that Ptolemy explained those kind of backward motions. He just said that the planet is orbiting the Earth, but basically it goes around these what are called epicenters. So it goes like this, and there'll be an epicenter here where it goes around. This is my indirect, okay, and then I'll go direct. This is my indirect, okay, so that's how I explain what we call retrograde motion. Now here's where, and I went ahead, just because I can, I have, I think, in this bag of these, those 3 slides we skipped, I went ahead and printed them off here. They're a little bit smaller, but here they are. There's 2 for you guys. The word, we get a lot of our words from Latin, and the word planet actually means wanderer. Wanderer. So one of the things about Venus, we'll pick on Venus, is that right now it's going through a constellation. I'm not sure what constellation Venus is going through. But if you were to watch Venus, it would actually move, it would move in a line in that constellation. It's not against the same background stars all the time. Venus is moving, okay, against the background stars. It's wandering, okay? And so this slide kind of talks you through, or is a look at, Mars wandering. So, let's see. Again, I can't even really make out what those background stars are, what those constellations are. But one of the cool things is, remember we talked about the constellations of the zodiac? Okay? And so planets generally move through those constellations of the zodiac. So it's probably one of those. But here it's showing Mars wander. Notice kind of the time scale. Okay, it goes June. Okay, this is what we call this. Oh, maybe better pick red. Here it's in direct motion. Okay, and so it's direct, 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 direct. Here it is July, and there about July in this particular year, I'll switch to green, it actually went backwards. It went backwards against the background stars. This green is the retrograde motion, okay? And I mentioned astrology, and then about September, it started direct motion again. So green is retrograde, red is direct, okay? I mentioned astrology because, bless you, astrology kind of goes like this. We can actually understand when the planets are going to do this in the sky, and it's supposed to have some influence on your horoscope. Okay. So direct motion, I'll kind of read off my slide here. I don't usually do that, but direct motion can be explained if the sun, okay, can be explained if the sun, if the sun, planets, and stars orbit the Earth. Okay? But this cannot explain the background motion unless you do the epicycle thing like Ptolemy did. And I'll kind of tell you what's wrong with Ptolemy's approach to these epicycles. A planet orbits the Earth. Oh, okay, I'll buy that. but then it has these little epicycles, it goes backwards, and then it continues to orbit. I'm like, I don't think so. Okay. So here we go. This is why we have that backward motion. This is why we had retrograde motion of the planets against the background stars. One of the things we're going to get to, probably not today, is Kepler's 3 laws of motion. And one of his laws of motion says that the farther the planet is from the sun, okay, the more slowly it's going to move in its orbit. Put another way, the closer the planet is to the sun, the faster it zooms around in its orbit. So here we kind of have that sort of thing. If these are both planets, the person with the blue shirt is going faster than the person with the red shirt. So what they've done in this figure is basically take that person in the blue shirt, looking at the person in the red shirt, and kind of put a position out there on that ribbon of where, against the background, the person in the blue sees the person in the red. So for instance, here, the person in the blue is going faster. Here, the person sees the person in the red here, okay? It's a line of sight sort of thing. Here, it sees the person here. That's direct motion. At position number 3, it sees the person over here. What happens with retrograde motion is this person is going faster. Now, over right here, comparing 4 and 5, I say the person on the inner track overtook the person on the outer track. Basically went past him. Now, he looks out there at the red shirt person, and he sees the person go from 3 to 4. That's backwards. That, not backwards, but that is backwards. Okay? And then after he's finished overtaking him, then he starts to see from 5 to 6 actually is back to direct motion. From 5 to 6, okay, now that's direct. So we have direct motion. Now it's kind of similar, I don't know if you guys can relate to this, not that you should be speeding down the highway or anything, but let's just say you're in the outer lane and you're going to pass somebody. You're coming upon somebody and you're going to pass them. And it's almost a strange sensation, okay, if you kind of glance at that car you're going to pass against the background, okay, you're both moving, okay, and you kind of see them, oh, you know, it looks like they're kind of moving this way, okay. As you kind of catch up with them, it kind of feels like for just a minute they're moving in the same direction you are, and then they go back to moving like that. It's kind of weird, but that's kind of, I've felt that before. So I bet you have too.
She was
Semi-drivers?
It's longer.
So this actually switches, the person in the blue would be us, and the person in the red shirt would be some sort of planet that's moving more slowly than we are, for instance, Mars. Okay, so the backward motion of Mars. Okay, so I know, it's kind of something to wrap your mind around. But here finally, do you guys get this? And I'll put this under here. I say this explains retrograde motion. Retrograde is that backward motion. There you go. Now we should be back to, is this your next slide? No, this is not your next slide. This is, oh, this is neat too. So the problem with this is if, and it is the case, if the planets are orbiting the sun, then we're changing our position. Then those sets of stars that we love, like Leo and the Northern Cross and the Big Dipper, then as we move, and they are different distances from us, they should make different patterns in the sky, just because. Okay, just because. It's called parallax, parallax. So for instance, showing you parallax is if this is the heliocentric model, this is the sun-centered model. In here, right here, okay, if we look at this star, okay, actually it should look kind of over here against the background stars. So purple all goes together. Okay, here you see the star, it looks like it's here against these background stars. I'm going to switch to red. 6 months later in January, okay, we look at this star against the background and notice that it's now over here. Okay, that's parallax. It moved. Why did it move? Because we moved. Very common way, and everybody has to do this. Let's see. So I'll stand back here so you guys can So everybody take your finger and put it, let's see, how do I do it? Put it kind of close to your nose, okay? And close one eye and close the other eye. Close one eye, close the other eye. And if you want to, you can kind of look at the screen. Okay, when I did that, and you should have a dominant eye, the one where it moves the less is your dominant eye. For me, when I went back and forth, I mean, I saw my finger here and here. Okay, so that was about here. Now, take your finger and move it twice the distance from your nose. And wink. Okay, when I did that, I got like this. I went from here close to my nose to here. So now take it and move it the distance of your arm and close one eye and close the other eye. It went down a little bit, but it's still kind of here and here. So that idea of you kind of changing your eye, okay, you are kind of looking at it from different positions, okay? And the farther away it is, the less it changes its position against the background. Okay, that's parallax. So the thing is the farther you get it away, then you don't see parallax happen. Okay, we're all going to want to go out and be eye doctors. The farther you get it away, then you don't see parallax happen. So one of the things that Galileo found out, and we'll hit this on Friday, one of the things Galileo found out is the reason we don't see parallax is those stars are so far away from us anyway. And even though the Earth is, 6 months apart in different locations, there's no parallax. Okay, I guess we're going to get to stop there. So we'll finish up this chapter, I know, on Friday. Fabulous Friday.